All right, so today we're going to talk about normalization in databases. Before we get there, we have been talking a little bit about relational schemas and how we're going to be drawing those relational schemas. I'm going to encourage everyone when you work on relational schemas to use a specific template in Lucidchart, and I'm going to show it to you, and I'm going to talk about why. This is something new, but I think this is going to be important from a convenience standpoint moving forward. So the template I'm going to encourage that everybody use is the ERD import example. If you search for a template in Lucidchart, you'll be able to find this ERD import example, and you'll see it. It's got this event stuff, the questions, event logs, all that sort of thing. None of that's relevant to any of the problems we're doing, but the structure of this is what we want. And here's why I want to use this. It doesn't quite lay out things the way we've been doing it sideways. It does it up and down, but that's perfectly fine. And in fact, it kind of works well on the computer screen in terms of organizing things. It specifically adds some additional coded information. So if you see the PK here next to event question ID, PK stands for primary key, FK stands for foreign key. So it's very spelled out what's primary key and foreign key, and it's not doing it with underlines or dotted underlines. It's doing it with that primary key designation. And if you do have a situation where you have a combined primary key, like you do down in event team, you'll see that PK, where they are the combined primary key, and each one of them by itself is a foreign key someplace else. Well, that tells a whole story right there. So that's really nice. We have the names of each of the different attributes in each one of these rows. And then we have what kind of data we think that thing's going to be, whether it's going to be a number or it's going to be text, there's going to be some sort of time date stamp or some sort of user defined field. And that's all pretty nice as well. These tables that are pre-set up for you have a couple of nice features. They have this shaded header, which you can turn on and off, which is basically the name of our entity if we were creating entities. And you can just double click on that name of the entity and change it to whatever you'd like. It has this alternate row shading, which makes things a little bit easier to read inside the table, which is great. You can, when you have one of the tables or relations highlighted, you can add additional fields by just increasing or decreasing the rows, which again is really nice. You can create a new one and just copy and paste this, or increase or decrease this, which is really cool. Again, you can double click anywhere and type over whatever is in here. But here's where the real magic happens, is after you create all of your relations and you draw all the relationships between your relations and you do mandatory or optionals or what have you in each of the different directions, we will eventually be able to click on the export button off to the left-hand side. And we're eventually going to be using SQL Server. We have a SQL server available to us in Maze. And I'm going to get all of you accounts set up later in the semester. And this will set up the initial code to initialize your database. So things like creating the tables, creating indexes, creating other tables. It's not going to be perfect. We're definitely going to have to take this and potentially change it and adjust it a little bit. But it's way better than having to do this from scratch. Imagine having to type all of this code absolutely from scratch. It's a pain in the neck. But if you are able to use Lucidchart to generate this stuff to start with and just copy and paste it and then edit it from that starting point, that's going to be a huge step forward. So we'll be able to take some of our earlier diagrams that we're doing here this next week or two, and we'll be able to transition them into a SQL Server without nearly as much effort. So when you are working through the next set of workbook problems, and we'll talk about that today, I want you to use this as your initial template. That means you'll probably be able to delete a bunch of these tables. Over to the side under entity relationship, you can then add them back in. I'm going to suggest the 3-column entity because that allows you to put the primary key, foreign key information, all that sort of thing. You might also want to just copy and paste an existing table template that has all that format and play around with it. So you're going to have to use this template a couple times to get used to it, but this is a great place to start for our next step later when we're going to be transitioning to a real database. Okay, hopefully that makes sense. Everybody's good on this. All right, so for the remainder of today, I'm going to talk through normalization. We're going to keep today kind of short. This won't take particularly long, and then I'll let you guys go. And like I said, I'll see you in a week. But I definitely want to talk about normalization. And it's funny, you'll see this slide deck looks a little different than some of my other slide decks. I didn't change it. I haven't changed it on purpose because it is a little bit anachronistic. And I want that because I think it's kind of interesting. Where's my, hold on a second. I went and looked at the metadata for this slide deck, and this slide deck I originally started writing in 1998. So this slide deck is older than most of you. And it hasn't changed that much since then, which tells you a little bit about how database relations have worked, how a relational database is actually structured. This is fairly similar material to what I've been teaching for 23 plus years. So it's still relevant, still interesting, but definitely a little bit long in the tooth as far as the format of the slide deck is concerned. But it works, so we're gonna make this work. So let's talk about normalization. For a well-structured database, and again, we're talking a reasonably small database. We're not talking the huge databases that companies like Twitter or Facebook or Google use to manage all their data. Something that's more manageable for a department in a company, something along those lines. We want our data to follow normal form rules. We want to normalize all of our data. And the goal here is to make sure that the data in our database is really easy to process, to store, to ensure validation, so things that get into the database are exactly what they're supposed to be, to make sure we're enforcing integrity rules, so things like a customer has to be in the database before they can buy something, that kind of stuff. We're also trying to eliminate any redundant data. We don't want things stored in multiple places. And I will bring up an aside here. I think this is a particularly interesting point that's going on with me today. If you look on my little thumbnail video, you can see that my name right now is Boone II, comma, Ted. There are multiple places at Texas A&M where they store your name. My formal name, no thanks, Dad, is Edward Francis Boone II. Anyone who's thinking about naming their child the second or the third or junior, ask someone who has a name who is a second or a third or a junior, and they will tell you, do not do that. It's a pain in the neck. I have to have a legal name inside the system, which is my full name. I also have a preferred name, which is what everybody has called me since the day I was born, which is Ted. I'd like my name to say Ted Boone. It says Ted Boone II. No one at Texas A&M can figure out why. Would I like to fix that? Yeah, and part of that is redundant data, right? Stored in all kinds of places all over the place, and nobody can seem to figure out why that second is showing up in Zoom and showing up in my email, even though it shouldn't be. So we'd like to eliminate that. This is a great example of poor database management. We also want to make sure that any data dependencies where data is linked to other data points make common business sense. I've alluded to this before. I've talked about how we might have some rules in our database that have been established, but they don't actually reflect how the business works. We want to try to avoid those if at all possible. If there is a rule that's inside the system, we want to make sure that rule is being properly enforced based upon business sense. Yeah, this is a different slide deck. I want you to pay attention to it. I will post it later today, but I just wanted to tweak it before I actually posted it. So you'll see it up on eCampus a little bit later today. But just watch what I'm doing here. Obviously, you can follow along with the video at a later time as well. So normalization follows a series of steps. These are building blocks. Once you establish first normal form, then you can move on to second normal form, and then third normal form, and even fourth and fifth. But we're going to really stress the first three normal form steps. The first one is by far the biggest one. What we're trying to do in first normal form, you'll also see it abbreviated 1NF, is eliminate what we call duplicative columns from the same table. If we have them in our original data, a lot of times our data is coming from a spreadsheet or a web page or maybe a piece of paper. If we have duplicative columns, we're going to want to get rid of them. Duplicative in this case is different than repetitive. We're actually going to see a lot of repetition in a well-formed database, but we won't see a lot of duplication. So we're going to be very careful about that, and I'll show you some examples of that. We're also going to create separate tables for any group of related data, and then identify each row with a unique column or set of columns that's called our primary key. And we're familiar with some of this terminology, but we'll revisit it as we move through things today. So the first rule, we can't have duplicate data within the same rows of a table. Technical term for this is the atomicity of a table. We saw this in our slide on Tuesday. We talked about an atomic table. It's basically as small as it can be. There's no way to further consolidate it. If there's room for consolidation, if there's information that's being stored across multiple columns that could be combined into a single column, you gotta be careful about that, without any duplicity, then we want to do that. So we're going to take a look at how we can make a table atomic. Here is a common situation we would see in somebody's spreadsheet that's storing managers at a company and their subordinates. And for a simple spreadsheet in a small company, this is absolutely fine. Bob has 3 people working for him, Jim and Mary and Beth. Mary has 4 people working for her, Mike and Jason and Carol and Mark. And Jim has 1 subordinate, Alan. There's no problem there from a small structure standpoint, but if we want to build this into a database, this structure has some issues. Subordinate 1, 2, 3, and 4 are effectively equal to each other, but there's some suggestion, since they are different columns, that they might be different than one another, and that's a problem. We don't want to suggest that Jim is more important than Mary or Mary is more important than Beth. The other issue is that you can imagine a situation where one manager could make this table look ridiculous. What if out of 4 managers, most of them have 2 or 3 subordinates, but one of them has 35? What you end up with is a table that's super wide to accommodate that one manager. Most of the information on the table is blank, right? Most of it's empty because most of us have 2 or 3 subordinates, and then subordinates 4 through 30 are empty. But that one manager has 30 people that are working for it. That's a mess. That doesn't work particularly well. And we definitely want to avoid those empty spaces because they actually do end up taking up space on the computer. They end up taking processing power. So anything that's empty is a little bit cost prohibitive in bigger databases. We want to try to get rid of that. So anytime you see a situation where you've got some blank spaces, you might be looking at a situation where you've got some duplicative columns. You're going to want to think about how you might be able to fix that. Now, there are people out there in the world, and I have dealt with them, that know just enough about this to make a dangerous mistake. So I want to be careful about this. I can see that subordinates 1, 2, 3, and 4 are duplicative. I want to try to shrink this data down to a more atomic level, get it a little bit more tight inside the storage, because I want to avoid things like when Mary adds a subordinate, I have to add an entirely new column. And in fact, that's going to be a rule we follow in our databases, is when we're adding or removing data, transactional data, actual information, not metadata, not changing the structure of our data, but actually adding information or removing information. The only way that we want our data to change is up and down. If I'm going to add somebody, it's going to be a new row in a table. If I'm going to delete a sales item, it's going to be deleting a row in a table. I'm not going to be ever adding or deleting columns. That's going to be something we do structurally for the design of the database, or maybe very occasionally for a restructure of the database. But in terms of day-to-day activities, the only change in the database will be up and down as we add and delete rows in the table. In this case, if Mary wanted a new subordinate, the table would have to get wider. We don't want to do that. We want to make sure the table never gets wider or narrower in a day-to-day activity. So this is what people who know just enough about normalization do, which is dangerous, which is they say, fine, I'll come up with one column. It's called subordinates. Bob has Jim, Mary, and Beth. Mary has Mike, Jason, Carol, and Mark, and Jim has Alan. This is not what we mean by atomic. In this case, there are multiple names in the same entry. We talked about this on Tuesday. We talked a little bit about how sometimes a comma is part of one piece of information, like your address, but sometimes the comma is representing the separation between multiple pieces of similar information. And when that's happening, we have not gotten to an atomic column. This is not what we're trying to do. This is really challenging from a computer standpoint to sort, to add, to remove. If I wanted to sort the names for Mary's subordinates, how do you do that inside that single field where you rearrange them with those commas? That becomes really difficult. How do I add somebody? How do I remove somebody? And then what happens with those comma separators? How do you count people up? It becomes really, really hard to manipulate. So this is a bad deal. We never want to do this. Every piece of information should be singular piece of information in a cell, basically in a table. If you have more than one piece of information in a particular entry field, you've done something wrong. So what we want is something like this. Now, like I said earlier, the result of normalization does result in what we would probably think of as repetitive, right? Bob shows up 3 times. Mary shows up 4 times. Jim shows up, well, just once. But in this case, when we want to add an additional subordinate, we don't have to make the table wider or narrower. We just add another row at the bottom of the table. Mary gets 1 more subordinate, and Ted starts working for Mary, right? And that means adding basically the boss and the subordinate. So we're adding those 2 pieces of information, and that's it. So as this database gets large, if Mary decided to hire 30 people, instead of having 30 columns with a bunch of empty spaces and a lot of inefficiency, we would just add 30 more rows for those 30 new employees, 60 new cells, basically. And this is a really efficient way to store things. It's super easy to sort. I could sort by manager. I could sort by subordinate. It's super easy to add or remove. It's easy to count things. This is much more easy to manipulate. So this is not necessarily intuitive for people who've never dealt with databases before. This is not the way we typically think about storing information from just a writing on a piece of paper kind of thing. But from a computer standpoint, this is a way better way of storing things. And as it ends up in larger databases, being a much more efficient way of storing information as well, because there's not a lot of wasted space, and we can easily find the information that we want, sort it, to add it, delete it, all those sorts of things. Now, the second component of first normal form is that every row has to have a unique identifier. Manager, in this case, is not the unique identifier, right? Because we see Bob 3 times, we see Mary 4 times. So we can't use that as a unique identifier. We could potentially use subordinate, but am I crazy about using someone's first name for a unique identifier? It would be really easy for us to have 2 Jims or 2 Marys or 3 Jasons. So that's probably not a good selection choice either. So what we would want to do is probably use subordinate as the unique identifier, but use some sort of employee ID instead of somebody's name in this database. And then I could go look up subordinate 143 and figure out what their first name is, their last name is, their phone number, all that kind of stuff. Yeah. But in this case, subordinate's probably a good choice because each subordinate can only have 1 boss. And then each boss could potentially have a bunch of different employees working for them. Every time I've ever given this lecture, it reminds me of Office Space. If you are a student at a business school and you have not watched the movie Office Space, I think you shouldn't be allowed to graduate personally. You need to go watch this movie. But there is a scene where he talks about how he has 8 bosses. This database would never allow that to happen to the main character. He'd only be allowed to have 1 supervisor in this database. And I like that rule. That's typically how it works, is you have 1 person that you answer to. But the boss obviously could have lots of people potentially answering to them. And this clarifies some things as well, because you can see in some cases that a boss for 1 person is a subordinate for somebody else. So if you see a number like 201 answers to 182, 201 also has a bunch of people working for them. So you can actually start to see the hierarchy, which is kind of useful as well. So it clarifies some things. So first normal form, anything that's duplicative, we need to bring down to a single column if at all possible. That might mean making the table a lot longer, a lot more rows in the table. That's perfectly okay. We want to make sure that we have 1 column for 1 kind of piece of information, if at all possible. And then unique identifier for every single table, whatever that might be. You might have to create a unique identifier of your own, but maybe there's something you can use that's already in your database. You have to think about that a little bit. After establishing first normal form, you can establish second normal form. These are building blocks. You can't have a database that's in second normal form, but doesn't already follow all the rules of first normal form. When you have a database that's in 2NF, that assumes that it's already followed all of the 1NF rules and guidelines. So for second normal form, we're removing additional subsets of data that might apply to multiple rows of a table, kind of moving them off to their own separate place. I love this step. I think this one's really cool. And we've only talked about this, kind of hinted at it a couple times this semester, but we've not actually seen it in action. So I think this one's worth taking a quick look at. And a great example of this would be storing customer information. for customers, we're probably going to have their last name, their first name, and we're going to have something about where they live. But when we look up where they live, really all we need to know about your city, state, and zip code is your zip code. If I say to you that I live in 77840, you know that I live in College Station, Texas. If I told you that my zip code is 90210, where do I live? Beverly Hills, California, right? If I tell you that my zip code is 19810, that's Wilmington, Delaware, where I grew up. So by knowing the zip code, I know the city and the state 100% of the time. And you've all experienced this. There have been times where you've been on the phone with somebody, or you've been on a web page and you've been typing stuff in, and you type in your zip code and it automatically fills in the city and the state. And think about all the other things that might fill in with the city and the state. It might also know, based on your 9-digit zip code, your exact region within that city or state. It might know some demographic information. It might know how much shipping is to that zip code. It might know the area code for landlines, so those are a bit anachronistic as well. There are all kinds of things that are associated with that zip code. So that one piece of information represents lots of other information. It is possible to make this table much smaller and more efficient by letting zip code be a surrogate for everything else that's associated with zip code. And the way we would do that is we would take that duplicative data. Now, this is duplicative kind of up and down as opposed to sideways, but it's still duplicative. And we would pull it off to its own. Now we see zip code in two places. You're like, well, now this is worse, not better. Not done yet. We would then take that pulled data and we'd shrink it down. Now, in this example, we have 5 customers. How many businesses have 5 customers? Even the smallest businesses have 500 customers or 5,000 customers. Big companies have thousands, hundreds of thousands, millions of customers. So you can imagine if I could just take 2 columns from a table that is 1,000,000 rows long, how much more efficient that database can be. And what if it's more than 2 columns? What if it's 16 columns of demographic information and shipping information that I shrink down to 1 zip code? You tell me your zip code and I can look everything else up. And where I go look it up, each zip code is just typed 1 time, right? So I had 11579 filled in twice up here. I had 33157 filled in twice up here. Well, now I only have to have it represented 1 time. So the zip code table becomes quite condensed, and the place where we were storing zip and city and state becomes much narrower. We store much less information in the customer table, and the overall database becomes a much more efficient thing. At any point in time, can you figure out what we earlier had and report it? Yeah, of course. Anybody in this classroom right now could tell me where Sue Ryan lives. You just look at these 2 tables and you say, she lives in Miami, Florida. The computer can do that even faster than you can. So this is a much more efficient way of storing information. If there's a situation where we could use something like zip code as a surrogate for additional information, we should. And we've seen some examples of this earlier in class. So we've had some situations where for the customer, we're storing certainly their street address, and then we've had city and state and zip. We might just move city and state off to someplace else. Strictly speaking, from a normalization point of view, if it's in second normal form, you would not store city and state in the customer table. You'd store it in a zip code table. So I like this one. I think it's really kind of cool to think about how much more efficient some things could potentially be. Anytime we want, we can go back and look. Anytime we want, we can generate a report that looked like that original table. It'd be easy to do, but nothing would be hard-coded and stored in our database in that format because it's not particularly efficient. All right, third normal form, which builds upon the other 2, is actually the easiest one. Anything that's not directly dependent upon the primary key, you get to remove. And what I mean by that is the only way I would know that piece of information is because it's typed into a table. If there's no other way to figure that out, then I have to type it. But if I can figure it out, I'm going to get rid of it. So the easiest way I can think about this is anything where if you were on an Excel spreadsheet and you're going to type an equation, if you type equals and then a cell times a cell or a cell plus a cell or the average of 3 cells or whatever, you're typing some sort of equation, you delete it. From a database standpoint, anything that would be calculatable, you yank it, it's gone. So in this case, for a particular order, which is the unique identifier for this table, there's a customer that placed that order. That's a foreign key that we can go look up that customer's name, and we can look up their zip code, and then that's a foreign key where we go look up their zip code to figure out their city and state. Yeah. So maybe you can think about the ERD you would draw for this. I would also know the unit price and quantity for that order. Apparently we're selling one product, and we're selling 2 of them for $10 for this particular customer. And so the total would be 20 bucks. In Excel, what would you be typing over in that total column? You'd type equals, basically the unit price column, let's say C2 times the quantity, D2. That total column is something that is calculatable. It is not dependent upon the primary key. So it's something that we could remove. We would just kill the total column. From our storage, at any point in the future, if you want to know how much this order's total is, could you figure it out? Yeah, you'd write a query basically that says unit price times quantity, you'd output it as total, no problem. But you wouldn't store it in the database, you'd calculate it after the fact. So third normal form is super easy. If it's something that would involve an equation in spreadsheet, that's my kind of litmus test. I get rid of it because I can calculate it after the fact. This is what it would look like if we were actually typing queries, and we'll get to that point later this semester. There is actually a fourth and even a fifth normal form. Fourth normal form is also called Boyce-Codd normal form. And what it means, or what it suggests, is that every relation is in Boyce-Codd normal form if and only if every determinant is a candidate key. We're not going to do fourth normal form in this class. That gets a little bit beyond what we need to figure out. So don't worry about fourth normal form or even fifth normal form, which is very strict. Most modern databases actually don't bother with fourth and fifth normal form. They're extremely strict in terms of what has to be allowed in the tables in the database. And as a consequence, it makes enforcing realistic rules kind of challenging. So most databases do get to third normal form, which means they have first and second normal form rules established, but they don't go through fourth and fifth. So because we're not going to see that in the real world, we're not going to do it in this class for the most part. But do keep in mind, when we do our databases, we are going to pursue third normal form guidelines, which means all 3 of those steps are required for any databases we work on in this class. Okay, so this plus our lecture from Tuesday gives us some structure for what we're going to be trying to do for the remainder of this next section. So let's take a quick look at what we're going to be doing kind of moving forward. We've got our, where is it? We got our workbook. And so we're not going to meet next Tuesday, but next Thursday, we're going to start working through the next set of the workbook. So we kind of left off, we didn't do all of these up to 15, but these are all regular ERDs. Starting with problem 16, we move into the relational schema. And the first couple are taking ERDs, and we're going to translate them to relational schemas. So I want you to take this drawing in problem 16, and I want you to translate it to the lucid chart template that I just showed you, and get the various fields put into the table, and get the primary key established, and get the foreign key established, and get the relationship established, and all that good stuff. So I want you to think about how you could take this ERD and translate it to a relational schema. And I want you to do that for all of the remaining problems in this workbook. I don't know how many we're necessarily going to get through, but I'm going to move through them kind of randomly next Thursday. So there are a bunch of them. They're mostly revisiting problems we've already seen. And I'm going to just randomly call on a group or an individual to work through these. So by next Thursday, I'm going to expect everyone, every individual in class to have looked through these and worked up some diagrams. If I randomly call you next week and you say, I've got nothing, then you're going to get dinged for not participating. You don't have to have the perfect answer, but you got to have something in terms of relational schema for next Thursday. Okay. If you want to, you are certainly welcome to coordinate with your teammates with general questions about, hey, I'm working on 17, I don't know what to do. What you're not allowed to do is say to your teammate, hey, what's your answer for 17? I'm going to write that down as my own. Right? I want all of you to go through the effort of trying to solve these problems by yourselves. It will be worth your time. You're going to have to eventually do it in an exam situation. So don't lean on your teammates too much. Make sure that you're doing this work by yourself. So if it's a quick question like, hey, give me a hint, point me in the right direction, and you want to reach out to somebody else in the class, that is certainly fine. But if it's anything more than that, if it's somebody showing you their screen, showing you their picture, sending you a file, you're not doing yourself any favors, right? For preparing for next week, you need to be working through some of this stuff on an individual level. Does that make sense to everybody? Okay. Any questions about anything we talked about today? Or any questions about our schedule coming up next week?
When I looked at the Lucid chart, I tried to pull up the data or the format that you were talking about, and it says it doesn't allow us to use it.
That may mean that you don't have your full educational account set up correctly, and you're gonna have to go through those, jump through those hoops to get that set up. Because it should be available to everybody, as far as I'm aware. So get with Lucid Chart. Again, you'll see some announcements about this. We've been trying to deal with this since the beginning of the semester. So you should be able to see that if you have the educational account fully set up. Any other questions, comments, concerns? All right, well, that's it for today then. I'm going to stop the recording.